In an effort to demonstrate consistency, I will try to always do each problem exactly the same way if possible, so that you can and employ a framework as we talked about in class, so that you have a place to start. So it says, a drive is inclined in such a way that rolling objects accelerate downward at 0.5 meters per second squared. This driveway has seams 2 meters apart. You watch a ball roll from somewhere above the first seam, and it takes 0.5 seconds to travel between seams. How far above the first seam did the ball begin its roll? Okie doke. So I need seams, so how about a seam every 2 meters? So a seam here and a seam there. Does that look like seams to you? So they are 2 meters apart. The ball started, say, here, and its initial velocity was 0. All right, so I'm gonna read the problem again. It says the acceleration down the ramp is 0.5 meters per second squared, and somebody's phone is muted. 0.5 meters per second squared, and the seams are 2 meters apart. It says that the ball rolls to here and has some initial velocity, I don't know what it is, and then rolls to here where I assume it'll be going faster with some final velocity, and that the time it takes is 2 seconds. I draw a picture. I think pictures are helpful. I try to label the picture with as many of the motion pieces of information as we have. So now I will start a framework. Delta X, VI, VF, AT. This set of motion variables represents the time that it's between seams. Is that okay? Delta X, 2 meters. Initial velocity unknown, final velocity unknown. Acceleration 0.5 meters per second squared. Time 2 seconds. Oh no, the time is 0.5 seconds. Sorry, everybody. The time is 0.5 seconds. So, how far above the first seam did the ball begin its roll? Well, I have 3 pieces of information, but they don't tell me about the stuff before I make it to the first seam. Do you guys agree with what I just said? That means there's probably a set of motion variables related to what happened before the first seam, when the ball was launched at rest and accelerated at 0.5 meters per second squared. This would be before first seam. Remember, your motion variables can only tell you about one interval in time and one acceleration at a time. I think there's 2 different intervals of time. There's the interval of time that takes place between the seams and the interval that takes place before we make it to the first seam. Does that make sense? Now I have 3 pieces of information here. I only have 2 here, and we want this. We want to know where it started. Can anybody think of a way that we might be able to use the information provided to get us 3 pieces before the first seam? Okay, maybe a little failure of imagination. Can you agree that the ball is going to start with an initial velocity here during that interval and speed up until it has a final velocity here? Does that make sense? Won't the final velocity here be the initial velocity here? I think that's the catch. I think the final velocity here becomes the initial velocity here. So let's find this initial velocity and use it in both places, right? I have to have 3 pieces of information. That seems like the best place to go. So I'm going to look for this. How's that sound to you guys? Is that all right? All right. Down the ramp, would you like that to be positive or negative? What's that? Negative? All right. So it went 2 meters down the ramp. The acceleration is negative down the ramp. Okay? So now I need a relationship that has all those things in it, but not final velocity. I think I have one. I think I'll use delta x equals 1/2 at squared plus vi times t. So -2 equals 1/2 times -0.5 times 0.5 squared plus vi times 0.5. Now I'm gonna have to erase all this because it's kind of in the way. Am I good to keep going? Is that all right? I'm gonna factor out a 0.5 and divide on both sides. That'll make that -4 equals 1/2 times -0.5 times 0.5 plus vi. Is that okay? So I just factored out one of the 0.5s. I have 1/2 times 1/2 times 1/2. That's -1/8 plus vi. All good? So I'm going to add the 1/8 to both sides, and I get vi equals -3 7/8 meters per second. Is that okay with you guys? Any questions about where that came from? All righty. I can apply that there. So I shall. Well, not there. I can apply that there. So I shall. -3 7/8 meters per second. There's probably a decimal for that would work just as good, but I don't really care. I think I can find delta x now. You guys see that okay? Gotta use something that has these 4 things in it. Says Florida is calling me. I assume the entire state. Let's go slide that over so I have a little room to work. I'm gonna go with v final squared minus v initial squared equals 2a delta x. So -3 7/8 squared minus 0 squared equals 2 times -0.5 delta x. I don't know what that is, but I'm confident in your abilities to figure it out. I'd have to do it in my head, and I don't want to. So do you guys want me to work out the numbers, or do you want to move on to the next one? Can I work it out? Well, sure. You tell me what 3 7/8 squared is, and then I'll do the rest. I don't have a calculator up here. I mean, I can convert it to an improper fraction and square it and all that, but is it?
Yeah, why it's negative?
Why is it?
Yeah.
Because we said down the ramp was negative. Once I said set the direction here to be negative, I had to apply that to any vector that was down the ramp. So the ball went this way, 2 meters, so I had to make that negative. And it said the acceleration was down the ramp, so I had to make the accelerations negative. The moment we said down the ramp was negative, all of those things had to be negative. Does that make sense? Yeah. All right, so what's 3 7/8 squared? You gonna make me get my calculator? Well, you don't have to be bold. So if that helps you, 3.875 squared minus 0 squared equals 2 times 0.5 is just negative delta x. So we're close here. 3.875 squared is 15. So not negative, 15 equals negative delta x. There's change, but who cares? Delta x equals negative 15 meters. So the ball descended negative 15 meters. That's a heck of a long driveway, right? So the ball rolls for 15 meters before it hits the first seam, and then the two seams are 2 meters apart. So that's our answer. Any questions about that? You said you were confused. Are you better now? Okay, you sure? All right. Shall we go on to another one? Do we have any other questions? Yeah? All right, number 9. Rock and roller coaster accelerates from rest to 30 meters per second over the length of coaster cars, approximately 12 meters. What is the acceleration experienced by the riders? When you shoot an arrow from a bow, it travels 0.75 meters, the length of the arrow, while accelerating from rest to 80 meters per second. What is the acceleration experienced by the arrow? Truthfully, if you were trying to ride the arrow, the acceleration would likely be fatal. All right, so I see 2 separate problems here, but the same information is given in both. So let's, I guess, start by talking about the rock and roller coaster. So, which I've ridden, it is a fun ride. So I think the idea here is that we'll just look at the last car of the roller coaster. It's accelerated the length of the cars just about, which they say is 12 meters. By the time we make it to there, we're traveling 30 meters per second. But here we have an initial velocity of 0. This must be the final velocity. All good? We want the acceleration of the system. So let's list out the given information. We can only apply the rules to one object at a time. So the cars are the first object. They accelerate 12 meters with an initial velocity of 0 and a final velocity of 30 meters per second. What direction would you like me to make positive? To the right or to the left? To the right is positive. So that means my 12 meters is positive and my 30 meters per second is positive. I would like the acceleration. So I'm going to find a relationship that has everything in it except for time. I believe the best way to go then would be v final squared minus v initial squared equals 2a delta x. That will be 30 squared minus 0 squared equals 2a times 12. This is 900, I believe, and this equals 24a. Just got to divide, so 900 divided by 24 gives me 37.5. You know, an acceleration of gravity is 10 meters per second squared, right? the acceleration due to gravity. We've been talking about that a little bit the last couple weeks. So you could say that rock and roller coaster accelerates at 3.75 Gs. You ever heard that phrase? How many Gs did you experience? That's how many times the acceleration of gravity. So our actual value is 37.5. A G is 10. So if you divide that number by 10, you get the number of Gs you experience during the acceleration. We'll be going to Busch Gardens Physics Day in a couple months. Montu pulls a lot more Gs than that, but it's not Gs are also pulled when you change direction. So most of the time, when you get a quote for how much Gs you experience, it's about a change in direction, not linear acceleration. All right, so I have to do the bow and arrow. So there's the bow. So it looks like that first, and then it gets shot, and we say the displacement between when it's shot is 0.75 meters, and it's going 80 meters per second after it's being fired, but the initial velocity is 0. So delta x, vi, v final, at. Delta x is 0.75 meters. Initial velocity is 0, final velocity 80 meters per second. What direction do you want to make positive? To the right or to the left? So positive and positive. All right, so I'm going to use the same relationship. 80 squared minus 0 squared equals 2a delta x. 80 squared is 6,400, and that equals 1.5a. So a is going to be 6,400 divided by 1.5, and I get 42.7. Is that right? Oh, poo. Divided by 1.5. Yep, 42.7. Meters per second squared. Of course, this would be, about 4.3 Gs. That's not fatal. You could survive that. So, you could survive that. Yay. Any questions? Yeah.
I put in 6,400 divided by 1.5, we got 4,267.
Oh, I'm probably just dividing wrong. Or I can't read my calculator. Let's see. 6,400 divided by 1.5. Oh, no, you're right. I just can't read this calculator. So, no, that would not be survivable. So 4,267 meters per second squared, or 430 Gs. Yeah, no, not survivable. The body can take about 15 Gs for short periods of time. There's been people in astronaut tests who have done more than that for short periods of time. Fighter pilots black out around 12 Gs if it's sustained. 15 Gs usually is fatal. The heart can't pump blood against the acceleration. So. But I mean, if you do it for car accidents, you can routinely experience a high number of Gs, but for a very short period of time, find that to be survivable in many cases. You'd probably find it uncomfortable though. 8. A rocket is launched from the ground with an acceleration of 20 meters per second squared for 1.5 seconds, and then the engine finishes where the rocket goes into free fall. What maximum height does the rocket reach, and what... I'm sorry, I need to go see. I see a problem that has two accelerations. There's the first part of the problem where the rocket has an acceleration upwards of 20 meters per second squared, where it does so until the engine's cut off, right? So during that time, it goes from an initial velocity of 0 to some final velocity. But then when the engine's cut off, gravity takes over. It's experiencing gravity, which is going to slow it till it has a final velocity here of 0. During that time, the acceleration will be due to gravity, which is downwards at 10 meters per second squared. I think there will be a displacement while the engines are firing, and then a continued displacement until the rocket is brought to rest. You guys follow that okay? All right. They ask a lot of questions, including what is the total time the rocket spends in the air until it makes it back to the ground. So let's find the first answer, which is what maximum height does the rocket reach? Well, remember, my motion equations can only handle one acceleration at a time, so I see two different accelerations. So I'm going to say there's this acceleration, delta x, vi, vf, a, and t. This acceleration is when the rocket engine is firing, and the acceleration is 20 meters per second squared, with an initial velocity of 0 and a time of 1.5 seconds. And then there's another acceleration that takes over after that. And during this time, the acceleration is 10 meters per second squared, and the final velocity will be 0 because it's brought to rest. Do you guys see anything that connects these two problems together? Yeah.
The final velocity of the bottom equation is the initial velocity that's on there.
I believe so. Yep. Now, we actually want this in both cases. Right? We want the two displacements. So, but I think we're going to have to find that. Right? We're going to need that so we can use it in the other part. So I'm thinking that's kind of the plan of attack here. Let's make upwards positive. That means this acceleration is positive, and this acceleration is negative. So I see three pieces of given information. I need both of the others, so let's just do them both. Delta x equals 1/2 a t squared plus vi times t. That okay? 1.5 squared is 2.25 times 10 is 22.5, so delta x is 22.5. Anybody want to check my math on that to make sure? Because I'm pretty sure 15 squared is 225. So 1.5 squared should be 2.25. And half of 20 is 10. So I think I'm right. But you should check. I also need the final velocity. So final velocity equals a times t. And that looks to be 30 meters per second. We all good? All right, tuck that away. This is now 30 meters per second, and it's positive, so it's upwards. I need delta x, so, well, I think I'm also gonna need t, but let's just do delta x first. I'm thinking 2 times a times delta x equals 0 squared minus 30 squared. So 30 squared is 900, and this is negative 20 delta x. So delta x is 45, right? Take out the 10 and it's 90 divided by 2, so 45 meters. So the maximum height sustained by the rocket is 45 plus 30, or 75 meters. That's delta x max, the whole thing. Any question on where I got the 75 from? Yay. Yeah.
Wouldn't it be 45 plus 22.5?
Oh, I added it to 30. That's probably a good call. Back it up. So 45 plus 22.5. Okay, so that's going to be 67.5. So delta x max equals 67.5. All right, I want the total time in the air. Well, I know the engine fired for 1.5 seconds, but I don't know how long it was in the air here. I'll have to find that out, but I'm pretty sure it's 3 seconds. But I'm just going to use a relationship that has those 4 things in it. So those 4 things would be 30 equals negative 10. Oops, sorry. 0 equals negative 10t plus 30. So t equals 3 seconds. So it takes 4.5 seconds to get to the maximum height. But, and you're not going to like this very much, there's another problem now. Delta x, vi, vf, a, t. Gravity brings the rocket back to the ground. It has to fall a distance of 67.5 meters. The initial velocity is 0 because it's at the very top of its flight. Acceleration is due to gravity, 10 meters per second squared. And we need time. I'm just going to make downwards positive for this part. That way it's all positive. I'll get the same answer, doesn't matter. So I need a relationship with those things in it. 67.5 equals 1/2 times 10 t squared plus 0 times t. So this is going to require a calculator. So I'll get 67.5 divided by 5 equals t squared. So 67.5 divided by 5, take the square root, and I find that it takes 3.67 seconds to make it to the ground. So all that together, time of flight, 3 seconds plus 1.5 seconds plus 3.67 seconds. Got to add all those together. So plus 3 plus 1.5. It is in the air for a total time of 8.17 seconds. Bless you. What do you think, quiz worthy? Just the same. Again, this is number 3, and it doesn't work. It doesn't slow down. And the speeds you get are astronomical. In fact, VI is already like 200 miles an hour. So not a particularly well-written problem. Oops, let's put in the distance of 1600 here. So if you work this out, take my 1600 and divide by 1.5, you find that this is 1066.7 equals 100 plus VF. So VF equals 967 meters per second, which is like 1,800 miles an hour. That's not particularly realistic, but okay. For working it out, that's what you would get. The acceleration is pretty crazy too. So this is how you'd find the acceleration. So 1,600 minus 300 times 2 divided by 9. You get an acceleration of 289 meters per second squared. 28 Gs, almost 29 Gs. So fatal acceleration for those 3 seconds. Yeah, not a well-written problem. Definitely not slowing down. I think it probably should have been 160 meters. That would be more realistic. That'd be a problem you could actually do. That would show something slowing down. But sometimes, you type fast and you get mistakes. I'll own this one. All right. How much more time do I guess, because we're completionists. And to point out that your homework can take under 40 minutes. you might not have been able to do it this fast, but have we done anything outside of the series of steps we talked about? They're all the same steps, right? So in a car accident, I'm not even gonna draw a picture. A car can go from 20 meters per second to rest. So initial velocity is 20 meters per second. Final velocity is rest. In a very short distance, let's assume that in a car accident, the distance it takes the car to come to rest is 1 meter. Delta x equals 1 meter. How long does it take for the car to come rest, and what is the acceleration? So two things we didn't do or didn't know. There's bound to be a relationship that has these four things in it. So I'm thinking delta x equals 1/2 times t plus initial velocity, 20, and final velocity, 0. So how long does it take to come to rest? Half of 20 is 10, so the time of the accident is 0.1 seconds, 100 milliseconds. What's the acceleration? I'll use one that has everything except for time in it. So 0 squared minus 20 squared equals 2a times 1. 20 squared is 400, divided by 2 is 200, so the acceleration is negative 200 meters per second squared. Not fatal, but you're gonna be probably in the hospital for a while. 20 G's. This is assuming that you stop in the same distance the car stops, so that means, the dash brought you to rest or something like that. Now, the whole idea of the car taking a meter and you taking an additional meter says that it can give you twice the distance to stop in. So that just changes the problem from having a displacement of 1 meter to a displacement of 2 meters. That's it, same problem. So 2 equals 1/2 times t times 20 plus 0. So t equals 0.2 seconds. And 0 squared minus 20 squared equals 2a times 2. So instead of stopping you with an acceleration of 200 meters per second, it looks like it's going to stop you with an acceleration of 100 meters per second squared. That's half the acceleration. That means half the amount of G's acting on your body, more survivable. The longer you can take an accident to take place, the fewer accelerations you experience. A drive is inclined in such a way that rolling objects accelerate downwards at 0.5 meters per second squared. This driveway has seams that are 2 meters apart. You watch a ball roll from somewhere above the first seam, and it takes 0.5 seconds to travel between the seams. How far above the first seam did the ball begin its roll? So let's start with a driveway. And somewhere in the driveway there are 2 seams. Excuse me. And thank you. They are 2 meters apart. We know that the ball makes it to here after having rolled from someplace over here where the initial velocity was 0, but the initial velocity here we don't know, and we assume that it's getting faster because it's accelerating down the driveway with an acceleration of 0.5 meters per second squared, and the time that it takes to travel between these 2 points is 0.5 seconds. All right. Let's talk about what we know. Between the seams, we know the displacement is 2 meters. The initial velocity is unknown. The final velocity is unknown. The acceleration is 0.5 meters per second squared, and the time is 0.5 seconds. That appears to be 3 pieces of information. That means we could solve for either speed here, but that's not what the question wants. The question wants us to figure out how far above where I started the ball was started. So let's see what I know about that situation. Delta x is unknown, but the ball was started from rest. I don't know the final velocity, but if it's the same driveway, the acceleration should be the same at 0.5 meters per second squared, and I don't know how long it takes to reach the first seam. I believe this is all. I think this is all the information I was given. And the question is to find this. Now, we can use those motion equations to solve problems. However, those motion equations only work for one time interval, and they work for one acceleration at a time and one object at a time. I see two different time intervals. I see information about a time interval that I know about, but I'm not interested in, and information about a time interval that I don't know much about, but am interested in. So, is there any way to connect these two things together?
Yes.
How?
Isn't the distance between the two 4?
No, I don't know that.
From beginning and start, so wouldn't the other one be 2 meters as well?
I have no way of knowing that. It doesn't say that. Yeah?
Would the V final, like the one on the right, be the V initial of the one on the left?
Sure. The ball rolls from here to here, acquiring velocity. So the final velocity for one interval becomes the initial velocity for the other. So if I can find this, I can plug it in there. That's how this problem is done. It's a two-part problem where the end of one part helps the other. So the truth is, I'm going to do that in reverse. I'm going to find this initial velocity and plug it in there. That's the trick, and it's not a trick. It's just what happens. So, down the ramp, do you want it to be positive or negative? It's your problem.
Oh, sorry. Negative?
Okie doke. Down the ramp is negative, so the ball travels negative 2 meters with an acceleration of negative 0.5 meters per second squared. I have to apply the direction uniformly to everything. I don't really care about final velocity. I only want initial velocity, so I'm going to choose a relationship that has all of those things in it. I think I will take delta x equals 1/2 at squared plus vi times t. And that will be negative 2 equals 1/2 times negative 0.5 times 0.5 squared plus vi times 0.5. All good? I'm going to factor out a 0.5 because I have so many of them and divide both sides by 0.5. That'll give me negative 4 equals 1/2 times, oops, this acceleration is negative, don't forget that, negative 0.5 times negative 0.5 plus vi. So I just divided out by 0.5, which was like multiplying this side by 2. Okay? Any question about that? Oh, good. 1/2 times 1/2 times 1/2 is 1/8. So this is negative 4 equals negative 1/8 plus vi. So vi must be negative 3 7/8 meters per second. Or if you don't like that, 3.875. Any questions? Well, that is this velocity, negative 3.875 meters per second, and my acceleration is also negative. So now I want to find the displacement. I'm going to use everything except for time, so that'll be 2a delta x equals v final squared minus v initial squared. So 2 times negative 0.5 delta x equals negative 3.875 squared minus 0 squared. But I'm running out of room, so. You just got to solve that. 2 times 0.5 is 1, so 3.875 squared I think is like 15. So I'm going to say negative 15 meters. So it starts 15 meters above where I am. Any questions about that? Perfectly acceptable question for a test. All right. A rocket is launched from the ground with an acceleration of 20 meters per second squared for 1.5 seconds, and then the engine finishes, where the rocket goes into free fall. What maximum height does a rocket reach? What is the total time the rocket spends in the air until it makes it back to the ground? So, rocket down here, rocket engine fires, starts with an initial velocity of 0, and accelerates upwards at 20 meters per second squared until the engine's cut off. But at this time, it has probably got some final velocity upwards. So it's going to keep going upwards until gravity brings it to rest. Eventually, gravity will bring it to rest, so its final velocity here will eventually be 0. During this time, it's in free fall, and the acceleration is downwards at 10 meters per second squared. Any question about where I got any of that stuff from? I'm expecting you guys can do this without too much difficulty. Looking at the amount of writing going on, I suspect that's not true. But have I done anything yet that is outside what we've talked about? I see 2 accelerations. Do you? So that means 2 sets of motion equations, because the motion equations can only handle 1 acceleration at a time. So I will set up a set of variables that goes with the bottom one first, and put in everything I know about the start of this problem. Let's see, I don't know delta x, but I know the initial velocity was 0. Don't know the final velocity, but the acceleration was 20 meters per second squared, and the engine fired for 1.5 seconds. Then, the engine cut off. The rocket kept going upwards. I know that at this time, the acceleration is 10 meters per second squared, and the final velocity will be 0. That's when it's at its maximum height. I want these two, so I know the total height of the rocket. Well, I can get one of them. I'm going to have a hard time getting the other. So let's start by choosing direction, because that's the next step. After I've gotten all the information I can from the problem, next step. Do I want upwards to be positive or upwards to be negative? You asked. If upwards is positive, then the acceleration of gravity will be negative. The upwards acceleration will be positive. I apply direction to every number in my problem. Well, I can figure out this one pretty easy. All right, I've got everything to do that. How am I going to figure out this one? Well, yeah, we're going to take whatever we get here and plug it in there. So let's begin. Now, this is just a plug-in fest. There's no physics going on after that. Once you know that, we're just trying to plug this into the right relationship. Final velocity will come from VF equals AT plus VI, which is going to be VF equals 20 times 1.5, or 30 meters per second. That will be the final velocity after the engine's cut off. That's the initial velocity for when gravity takes over. I need the displacement too, so I'm going to use delta x equals 1/2 a t squared plus 0 times t. Half of 20 is 10. 1.5 squared is 2.25. So that's got to be 22.5 meters. And it's positive, so it's upwards. All righty. We need delta x in the top, so I'm going to choose a relationship that has these 4 things in it and ignore time. So that's going to be VF squared minus VI squared equals 2a delta x. So 0 minus 30 squared equals 2 times negative 10 times delta x. 30 squared is 900. So this is negative 900 equals negative 20 delta x. So that's got to be 45, positive 45 meters. Total height of the rocket, 67.5 meters. Now, it also wants the total time that the rocket's in the air. Well, we know that the rocket fired for 1.5 seconds. We can probably figure out how long it took gravity to bring the rocket to rest, because we have all the information to do so. So 0 equals negative 10 times 1.5, no, not 1.5. Negative 10 times t plus 30. So that's 3 seconds. So 3 seconds, 1.5 seconds, total time to get there is 4.5 seconds. That's not the answer to the question, though. The answer to the question was total time in the air. The rocket comes back down. So I have to figure out how long it takes the rocket to come down, assuming a delta x of 67.5 meters, and an initial velocity of 0, a final velocity that's unknown, but an acceleration of 10 meters per second squared. I should be able to figure out how long it takes for the rocket to fall all the way back down. And if I continue with upwards is positive, that's negative and that's negative, because it falls downwards 67.5 meters with an acceleration that is downwards at 10 meters per second squared. So negative 67.5 equals 1/2 times negative 10 t squared plus 0 times t. So I don't know. You'll need a calculator. So you'll need to calculate that sucker up. It's going to be between 3 and 4 seconds, I'm pretty sure. But you figure it out. This is boring. I am bored. But I'm kind of done, right? You're going to find that number and add it to 4.5 seconds? Do we really have to do that part? If you don't understand what's happening now, you're probably not going to understand it on the test. But at the same time, if you have a question, you should ask it. By the amount of writing I'm seeing that people are having trouble. There's nothing particularly fancy here yet. All right. Is there anything else on the practice test that you would like me to go over? Go ahead.
Number 6.
You drop a rock off a tall bridge and hear it splash 2 seconds later. So I drop a rock, initial velocity 0, off a tall bridge, and I hear a splash 2 seconds later. How tall is the bridge? If instead you throw the rock upwards at 10 meters per second, how long until you hear the splash? Well, I probably need to know how tall the bridge is before I can answer the next question. So let's do the first question. You asked, so do you want upwards to be positive or downwards to be positive? Okay, so upwards is positive. Delta x, vi, vf, at. The rock is dropped. I hear it make a splash 2 seconds later. The acceleration is due to gravity, 10 meters per second squared, and that is downwards, so I make it negative. So let's find out how tall the bridge is. It's going to be delta x, how far the rock falls. Agreed? Alrighty. So delta x equals 1/2 a t squared plus vi times t. 2 squared is 4, half of 4 is 2, 2 times -10, -20 meters. The rock fell downwards 20 meters, so the bridge is 20 meters tall. So that makes this delta x 20 meters. Delta x is going to be -20 meters because the rock falls downwards 20 meters after it is thrown upwards at 10 meters per second with an acceleration of downwards of 10 meters per second squared. I don't know what the final velocity is, but we want how long it's in the air. I think there's one of those that will get us time, so let's use it. Delta x equals 1/2 times the acceleration, t squared, plus the initial velocity times t. So looking closely at this, I'm going to get 0 equals -5t squared plus 10 times t minus 20. Divide by -5, and 0 equals t squared minus 2t plus 4. Well, are there two factors of 4 that I can use such that they'll multiply together to give me 4 and add together to give me 2? I mean, my options are 1 and 4 and 2 and 2, right? So I just don't think I have the right combination, do you? So I guess we got one choice, quadratic formula. You guys know how to do that, right? All right, yeah.
Couldn't you graph it?
You could. I'm not going to teach people how to do that, but you could. Did you?
I did.
What'd you get for your 2 times?
I got 3.27 seconds.
3.27.
No, both of them. That was just my final.
Okay. It seems not unreasonable that if it took 2 seconds just to fall, it would take more than 2 seconds if it were thrown upwards. So, it looks like I made a mistake though. So if you put this in your calculator, you're gonna get the answer wrong. Can anybody point out where my mistake is? It's arithmetic.
Plus 20, not -1.
Thank you. When I add the 20 to both sides, that should be a positive. And when I divide by the -5, that should make this negative. I had a feeling I had a problem because I knew I would have to have one positive root and one negative root. When you do this problem, you'll get 2 answers. One is a positive time and one's a negative time. Throw the negative time away. Just keep the positive time. Should you have this on your test tomorrow, are you guys going to be successful with that? I'm not giving you the quadratic formula. You should know it. Oh, didn't record any of that. Oh well. It happens. So you people in other classes who watch this video, and I don't know why, I feel like we've gone over all of them. But there you go. Number whatever this was, 5. Right? Yeah, 5. The car went forwards 9 meters while slowing down from 3 meters per second to 0. If I want to kind of graph what that should look like, at 6, I should have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 meters. So this side here has an area of, let's see, this is 1.5 but negative, and this is 3, so 1/2 of 3 is 1.5, 1.5, so 2.25, negative 2.25 meters. So it's going to come back to about 9, 7, 8, somewhere right in here. I'm sorry, 9, 8, 7, so somewhere up there. Starts at the origin, so steep slope here, because that corresponds to the 3. 0 slope there, that corresponds to 0, and negative slope there, that corresponds to negative 0.5. Something like that. That's not great, doesn't look too parabolic, but better. So we want a model for the parabolic curve on the right. Well, the only function over there that models a parabola is 1/2 a t squared plus vi times t. There are only 2 models that I even talked to you about, and they are v equals at plus vi, and delta x equals 1/2 at squared plus vi times t. Those are the models for these 2 functions. This is the velocity function, this is the position function. So if I want the model for position, I need to plug in what I know. I'll probably separate this and make this x final minus x initial equals 1/2 at squared plus vi times t. It starts at the origin, so that's 0. So x equals 1/2 times negative 0.5 t squared plus 3 times t. We know the acceleration, we know the initial velocity, that's our model. And that's where it comes from. So I expect the answer to be x equals 1/2 of 0.5, so you can make it negative 0.25 if you want, t squared plus 3t. Probably worth 3 points, maybe 4. You had to know which relationship is a mathematical model from the graph that you made. You had to figure out the initial velocity and the acceleration and know that they were a part of this. To me, that's valuable points. Does that answer your question? All right. Just terribly, terribly boring. And I've been doing 5 hours of this today, of all the same boring garbage, just slightly different boring garbage in mechanics. But it's just all just. So here we go. I'll continue though, because I should not hold you accountable for what I've already done in other classes. So we'll start with the bridge question, and I will attempt to do every problem exactly the same way so that you can understand that I approach these all the same. Some of them do have, trick is the wrong word. Some of them you do have to be thoughtful about. Sorry to bore you, but none of them are all that terrible. So bridge, water under the bridge. You drop a rock off a tall bridge and hear it splash 2 seconds later. So it's dropped. That means the initial velocity equals 0. It is dropped, splash, and that takes 2 seconds. And we're ignoring the fact that sound travels back up to you at 330 meters per second. We're assuming it's instantaneous. How tall is the bridge? All right, so let's start with delta x, v initial, v final, a, and t. You asked the question, so you must answer the next questions. Ready? Do we know how far the rock fell? No. Do we know the initial velocity of the rock? Yes, 0. Do we know the final velocity of the rock? No. Do we know the acceleration of the rock? Yes. 10 meters per second squared. Do we know the time it takes for the rock to rake it to the ground, or to the water? 2 seconds. Do we have 3 pieces of information? Yes, we can likely solve for whatever we are missing. However, next step, do you want up to be positive or do you want down to be positive? Up to be positive. You have a question?
So for the acceleration of gravity, are we just always going to assume that it's 10 instead
No.
of 9.8? Or
Oh, instead of 9.8? Unless you're told otherwise, use 10. What's easier to use, 10 or 9.8? Use 10, it's easier. If we make up positive, then when I evaluate these, I don't have to evaluate the velocity, but I do have to evaluate the acceleration. It is downward, so I have to make it negative. Is there a relationship on the board that has those 3 things in it plus displacement? Believe so. It's the second one. So delta x equals 1/2 at squared plus vi times t. So delta x equals 1/2 times -10 times 2 squared. 2 squared is 4, half of 4 is 2, 2 times -10 is -20 meters. The rock fell downwards 20 meters, but that means the bridge is 20 meters tall. Question number 2, or question part B. Let's see, if instead you throw the rock upwards at 10 meters per second, how long until you hear the splash? So if instead I throw the rock upwards at 10 meters per second, assuming the rock goes up and then comes back down, how long until I hear the splash? Well, delta x, v initial, v final, a, and t. Do we know the displacement of the rock?
20 meters.
20 meters, that's right. It will land 20 meters below us. Do we know the initial velocity of the rock? 10. If we throw the rock upwards at 10 meters per second, so 10 meters per second, do we know the final velocity of the rock? Do we know how fast it hits the water? No, we do not. Do we know the acceleration of the rock? 10 meters per second squared. Do we know the time that the rock is in the air? No. Do we want upwards to be positive or downwards to be positive? If upwards is positive, the rock fell downwards 20 meters, thrown upwards at 10 meters per second, with an acceleration downwards 10 meters per second squared. Any question about the choices I've made? I believe we're going to use the same relationship here. So delta x equals 1/2 at squared plus vi. That'll be -20 equals 1/2 times -10 t squared plus 10. I believe that I can solve this for t. I'll move the 20 to the other side and get 0 equals -5t squared plus 10t plus 20. I can divide out by -5 to simplify this. And I'll get t squared minus 2t plus 4. Are there any... Oh wait, it's -4. Sorry, -4. Are there any factors that I can use for 4 that will multiply to give me 4 and sum to give me 2? I believe my only choices are 1 and 4 and 2 and 2, and neither of those will work, correct? That leaves me with -b plus or minus the square root of b squared minus 4ac divided by 2a, or use your calculator. I don't have a calculator, so 2 plus or minus the root of 4 plus 16 divided by 2. 4 plus 16 is 20, so that's 2 plus or minus root of 20. But root of 20 is 4 times 5, so that's going to be 2 root 5 divided by 2. So my answer is 1 plus or minus the root of 5. The root of 5 is bigger than 1. That would give me a negative number, so I know that one doesn't matter. So my real answer is 1 root 5, which, I don't know, probably 3 or 4 seconds. Took 2 seconds if I just dropped it. If I throw it up, I figure I'm going to add a second or so. What is 1 root of 5? Or 1 plus the root of 5? You guys have fancy calculating adding machines. If I beat you to it, you guys are slow. 3.24. Good job. Yeah, that's there's nothing wrong with that problem. There's nothing, I can expect you to be able to do that on tomorrow's test. Okay? And I think that is a confusing idea. But remember, displacement is absolute change in position. So it starts here, ends here, right? That's true. The path doesn't matter. The fact that it went up and back down doesn't matter. If we were to graph this, our graph would have looked something like this. Velocity versus time, something like that, with a little bit of a positive, but a whole bunch of a negative because it lands below where it is. Our displacement's still negative. It's going to be below where we started. That's all it is. Now, if they'd asked us how high the rock went or the total distance traveled by the rock, then we would have to figure out where it went above ourselves. But they didn't ask that. Now, there is another way to think about these problems if you want. Now, I don't know if I want to add complication to this, but just, I'll do it up here so that's out of the way. Delta x is negative 20 for this problem, right? But we could say that that is x final minus x initial equals negative 20. What do you want to be the origin? So if we say the origin is the ground, then an x initial is 0. That tells you that my final position is going to be negative from where I started, right? Or we could say x initial is 20 meters above where we started. You know, it's just, we're really just talking about what is the change from where we started. That's all it is. No big deal. Alrighty. So, anything else in the homework you'd like me to look at? A drive is inclined in such a way that rolling objects accelerate downwards at 0.5 meters per second per second. The driveway has seams 2 meters apart. You watch a ball roll from somewhere above the first seam, and it takes 0.5 seconds to travel between seams. How far above the first seam did the ball begin its roll? So, somewhere on the side, on this driveway, there's a set of seams that are 2 meters apart. The ball makes it here. I assume it's moving because it was rolled from someplace above here. So it starts with some initial velocity, and I assume that when it makes it here, it'll be traveling faster, and that this time was 0.5 seconds. And over the entire walkway, the acceleration is 0.5 meters per second squared. We are under the impression that the ball started somewhere above and was released from rest. So I am reminded that motion equations can only be used for one time period at a time, one acceleration at a time, and one object at a time. I have a single object, but I see two possible time intervals. There's the interval where we are watching it go between the seams. There's also an interval that we appear to know less about that took place before the ball made it to the seams. Would you guys agree with that? So I have a set of motion variables that have to do with the ball's passage between the two seams. I also have a set of motion variables that deals with the time interval before the ball made it to the first seam. In both of these, the ball was on the driveway, so in both of these, the ball had the same acceleration. It was released from rest somewhere above us, but during the time that it's between the seams, it takes half a second to travel 2 meters. Have I collected all of the information that was given and organized it appropriately? All good? All righty. Seems reasonable from this point to decide what direction we want to make positive. So would you like down the ramp positive or up the ramp positive? So you're the one who asked about the question. You want up the ramp to be positive? I don't care. We just need to pick one. Up the ramp positive. Okay. She asked the question. That's why I'm doing it. All right. If up the ramp is positive, then my displacement is negative because it traveled 2 meters down the ramp. The acceleration was down the ramp, so that's negative 2, or negative as well, and that makes it negative here. All right? What we actually want is this displacement. That'll tell us how far above the first seam the rock started. But I don't have 3 pieces of information there. And it takes 3 pieces of information to solve for a 4th. I could solve for either velocity here. Can anybody see a connection between these two things? What do you see?
The velocity initial of the first period times the final velocity of the second.
All right, so the final velocity from here will be the initial velocity here. Yeah, I think that's what you're trying to say to me. So the velocity that it acquires after rolling to here would be considered the final velocity for this set of variables. But that's the initial velocity for this set of variables. So if I can find the initial velocity here, I can use it there. You guys follow? Yes, I believe you're this smart. So let's do what we have to do to find the initial velocity here, and I don't care about that. I'm thinking -2 equals 1/2 times -0.5 times 0.5 squared plus VI times 0.5. Kind of cramming it in there, sorry. I can factor out a 0.5 and divide both sides and multiply both sides by 2 to get rid of it. That'll make this -4 equals 1/2 times -0.5 times 0.5 plus VI. I've just effectively taken and divided both sides by 0.5. Is that okay with you guys? 1/2 times 0.5 times 0.5 is just -1/8. This is -4 plus VI. So VI must equal -3 7/8 meters per second. It's negative because it's going down the ramp, not a surprise. If you don't like 7/8, then -3.875. So you asked me how many decimal places do you have to keep in your answers. In an intermediate step like this, you should keep as many decimal places as possible so you don't lose very much. But at the end, we are supposed to follow significant figures. All of the values have been given in 2 significant places, so I feel 2 significant places is appropriate. So that's going to be -3.875 over here. If I want delta x, I believe I could use 2a delta x equals v final squared minus v initial squared. All good? 2 times -0.5 delta x equals -3.875 squared minus 0. That's it, right? 2 times 0.5 is just -1, so I just need the square of 3.875, so 3.875 squared, 15. Delta x equals 15 meters. It's actually -15 meters because of the negative sign here. That just means that it's 15 meters up the ramp from the first scene. All right. Yeah. It's funny because I am pretty sure that all day I've been doing that and everybody's just kind of like, yeah, whatever. I know people can't do it. So it was -2 equals 1/2 times -0.5 times 0.5 squared plus VI times 0.5. Right? I factored out a 0.5. You don't have to do it this way. This is just how I did it. So I'd have VI by itself. But I have to get rid of that 0.5, so I divided both sides by 0.5. That gets rid of the 0.5 there, but what is 2 divided by 0.5? It's 4. Point 0.5 is just 1/2, right? So this is really -1/2 and 1/2. So 1/2, 1/2, 1/2. All okay? Yay. I don't think she's ready. Which part are you having trouble with there, kiddo?
I don't know why I'm having such trouble with that.
Well, then don't do it this way. Do it this way. Here. I mean, you have a calculator, kiddo. So, I mean, what if I just do 0.5 times 0.5 times 0.5 squared? Right? That gives me 0.0625, and it'll be negative,
Yes.
plus 0.5 VI at negative 2. You could do it this way. I'm just doing it on the board in front of you, and I just did the way I felt like it. But you asked, so I have to do it the way I want to do it. So I add 2 to that, and I'll get, so I get 2 minus 0.0625. That gives me negative 1.9375 equals 0.5 VI.
Sorry.
No worries. Right? So I divide this by 0.5, and I'll get that VI equals negative 3.875. See, math works. Yay.
Okay, I'm gonna do it that way.
You do it whatever way you freaking want. It's your this area that I've just identified here. You know, this would represent the displacement before the object stops, and that's 9 meters. This area would represent the displacement for the object's trip back down the track, and this is a negative, I think, 2.25 meters. And those are the two areas. So it seems to me if the object started from the origin, after 1, 2, 3, 4, 5, 6 seconds, the object will be 9 meters away from the origin. And then we'll come back 2¼ meters, so that's 1, 2¼ meters by the time we make it to the 9-second mark, which is there. At time 0, it's got a slope of 3. At time 6, it's got a slope of 0. And at time 9, it's got a slope of negative 1.5. So what's this going to look like? Something like so. That is clearly quadratic, so I should have a quadratic function to match. If I want to make this quadratic, if I want to make the function that matches this, I'm probably looking at delta x equals 1/2 a t squared plus vi times t. In fact, better yet, I should write this as x final minus x initial, but we started from the origin, so x initial is 0. But I know what a is. I found that from over here. It's the slope of the velocity graph, so it's 0.5. So this is going to be 1/2 times negative 0.5 t squared. And I know the initial velocity. I got that as well from that graph. That's going to be positive 3t. That's delta x. This is the function that matches the position versus time graph. In fact, you could do half of 0.5 and have negative 0.25 t squared plus 3t. So looking up there in the upper left-hand corner, those are the two models that match all the graphs we've made this year. The top model is for velocity versus time. The next one is for position versus time. There are other motion equations. They don't represent models. They represent either areas or things that we found by substitution, but they don't represent a graphical model.